So chapter 12 is about bonding, which is what that activity is on. And if I'm not mistaken, I believe we should be rolling into some activities next week as well on some naming. So I would anticipate that perhaps all these activities will kind of be due near the same time. And when we kind of finish them, we'll let you know when they're due. And that'll kind of give us a chance to catch up on some of this stuff here that involves naming and bonding. So we're going to talk about here chapter 12, which is chemical bonding. And really, when we talk about chemical bonding, we're going to be talking about two types of bonds, some of which we talked a little bit about today when we were talking about some of those periodic trends. But one type of bond that we're going to talk about for sure is an ionic bond. And when you have an ionic bond, it is always between a metal and a nonmetal. And really, because of those trends that we talked about today in lecture, those periodic trends, what we found out and what we talked about was metals have all those properties of they would like to get rid of their electrons. And nonmetals, on the other hand, have all the properties of they would like to gain electrons. And that's because, again, if you look on the periodic table, they're on opposite sides. We got metals kind of on the left, nonmetals up on the right. And when these two get together, they work out really well because the metal is just going to go take my electron. And what we're going to get always in this sort of case is an actual transfer of electrons. And the electrons will go from the metal to the nonmetal. The result of that is we will make a cation that is positively charged from the metal because it has lost electrons. We will make an anion out of the nonmetal, which is negatively charged because it gained those electrons. And one very important thing to remember about an ionic bond is there's actually no sharing of electrons here. It is solely what is referred to as electrostatic attraction. That's a fancy way of saying the positive and negative charges are attracted to each other. So what holds that together is no sharing of electrons. It is the attraction of the positive ion to the negative ion that holds that together. And that is always what will happen when you have a metal and a nonmetal together. So in the future, as you come across anything and you identify in a formula, for example, or whatever it may be, that you have a metal and a nonmetal together, it should always be this type of bond. It should always be an ionic bond where we have that transfer of electrons. Different than that, we're going to talk about in this chapter is a different type of bond, which is referred to as a covalent bond. And in a covalent bond, that is between two nonmetals. And again, if you just think about those periodic trends we talked about, and you think about the location of the nonmetals, all the nonmetals are pretty much at the same location on the periodic table. They're all up there in the upper right of the periodic table, which means all the nonmetals have exactly very similar periodic trends, which means all the nonmetals basically want to gain electrons. They want to keep their electrons. So when you get two nonmetals together, neither one of them wants to lay up their electrons to the other person or give them up. They both want to actually keep them, and they both want the other person's electrons. So the best that they could do in this situation is, because they both really want the other person's electrons and don't want to give up theirs, is they will actually share electrons. And that's the major difference between a covalent bond and an ionic bond, is you will get some sharing of electrons in this case. And as we will talk about, that sharing can be equal sharing or unequal sharing. But there is some aspect of sharing of electrons in a covalent bond. And again, that occurs because it is between two nonmetals, which again, they both, like I said, want to hang on to their electrons. So in this chapter, we're going to look at both of these types of bonding and sort of explain again what is happening with them. But ultimately, as we also touched upon in the last chapter, the goal of like all bonding is essentially to end up like our noble gases. Like we talked about the electron configuration, the goal of pretty much all bonding is for everybody to get to that noble gas configuration in terms of their electrons. And that's again because noble gases are really stable. And they're very happy that way. And that's really what happens in each of these cases. The way they're able to do that is different. and we're going to talk about that, but that is the ultimate sort of end result of each of these types of bonds. So we could use Lewis dot symbols to help us understand bonding, and Lewis dot symbols are named after a guy named Lewis, but sometimes nowadays they just generically call them electron dot symbols. But basically, what an electron dot symbol shows, or a Lewis dot symbol shows, is one dot for every valence electron. And remember that the valence electrons are the ones that are involved in bonding. The core electrons are not. And as we talked about in the last chapter, the number of valence electrons equals the group number on the periodic table. So again, that's a quick way to figure it out. Again, if you take a look at lithium, 1s2, 2s1, this is lithium's one valence electron from group 1, and these are his core electrons. So what Lewis dot symbols show is really only the valence electrons. We do not show core electrons in any type of bonding picture because they are not involved. So just those valence electrons equal to the group number. Basically, to draw a Lewis dot symbol is pretty straightforward. You use the symbol for the element that you have, and then basically you use one dot for each valence electron it has. There is no big rule per se as to how you put the dots around it, but the only kind of rule is no more than 2 dots per side. And since there's 4 sides, that means you could put a total of 8 valence electrons on a Lewis dot symbol. 8 is a really important number in bonding, and that's because if you go to the periodic table, group number 8 is the noble gases. Again, the whole point of what everybody's trying to achieve is those 8. Now, when we look at it here is some Lewis dot symbols for all the elements. I made one day when I was bored, so I should get a hobby. But this is group 1. Everybody has 1. Group 2, everybody has 2. 3, 4, 5, 6, 7, 8. Now, typically, a lot of times, like I said, people will kind of go, and again, there really is no rule, kind of just one at a time and then go back and kind of pair them. But it doesn't really matter as long as you don't go more than 2, and maybe get them closer than I did. There are a couple of exceptions in terms of sort of valence electrons. One major exception is helium. Helium is 1s2 is the electron configuration. It only has 2 electrons total, which means helium has only 2 valence electrons, even though it's part of group 8. So because helium only has 2 electrons, it can't have 8. It is still part of group 8, but it will only have those 2 valence electrons. Everybody else in group 8 will have 8 valence electrons. This is also why a really important aspect of bonding that people should keep in mind, because they screw it up all the time, is hydrogen. If I'm looking at hydrogen, and hydrogen's goal is to reach the noble gas configuration, who does hydrogen got to get to do that? It only needs to get to helium. And since helium only has 2 electrons, hydrogen should never, ever, 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 ever have more than 2 electrons. So you should never ever have more than 2 electrons to hydrogen unless you're like a big X. Yes, so don't do any of that. And I say that later on when we start drawing things. People for some reason just like to load up hydrogen, put dots around it, double, triple bond it. Never ever, yeah. So as you start drawing, hydrogen should only have 2 electrons. Basically, will look like that, where this line represents basically 2 electrons, yeah. And that's pretty much what it should mean. It also should mean you should never really find hydrogen like in the middle of things. It's usually on the outside, because if it's in the middle, it's going to have more than 2 electrons. So hydrogen is a really important one. And like I said, people do really kind of screw that one up a lot because, they just keep adding stuff to it. So no more than 2 for hydrogen, but everybody else, as you can see, pretty much in terms of our metals, need to go forward there, and our 2 group 8 guys, and our non-metals, our non-metals need to go forward, and our metals need to back up that way. So as I mentioned before, the two types of bonding that we could use sort of these Lewis dot symbols to help us is ionic, which again is our metal and nonmetal, and covalent bonding, where we have sharing of electrons between two nonmetals in this case. Yeah. Now, what these general rules that we sort of talked about in terms of periodic trends tell us is what we were talking about at the end. Pretty much, if you're kind of to the left on the periodic table and you're a metal, you typically like to give away your electrons and form positively charged cations. And if you are upper right of the periodic table in the nonmetal region, you have all of those trends that want to gain electrons, and you typically will gain electrons and become negatively charged or anions. So let's take a look at an example of ionic bonding. And by the way, I know this is ionic bonding because really the only two things I need to see to tell me that this is going to be an ionic bond is lithium is a metal and fluoride, which is fluorine, is a nonmetal. So as soon as I see that combination of those two things together, that should automatically scream in your head, this is going to be an ionic bond. It also should tell you that we are going to get, again, a transfer of electrons that's going to happen in this particular case. If we look at lithium on the periodic table, it is group number 1, which means because it's group number 1, it will have one valence electron, which will be represented by that dot. Its electron configuration would be 1s, sorry, 1s2, 2s1, and once again, that would be our valence electron. Fluorine, which is group number 7 on the periodic table, will then have 7 valence electrons around it. And if we do a little bit of its configuration, 1s2, 2s2, 2p5. Now, what we're putting together here again is a metal and a nonmetal, and always in that situation, our metal is going to give away its electrons to the nonmetal that wants to take them. And what's going to happen is we're going to get this electron actually transfer over to the fluorine in this case. It's at that point that the lithium has now lost an electron, and it will now become positively charged. Before, it was not positively charged until it gave away its electron, and now it will have a positive charge. Our fluorine, on the other hand, will actually pick up that electron, and it will go from 7 electrons to 8 now. And again, it will now become negatively charged as it did not have a charge to begin with. And now we have created an ionic bond here. So this is an ionic bond. It is the attraction between those things that hold that together. There is no sharing of electrons here. So when you draw sort of Lewis structures here for ionic bonding, they should have charges drawn on them to indicate that there is no electrons being shared here. You should also, perhaps like I did, put at least one of them in brackets, and sometimes everybody will put everybody in brackets, but at least one of them probably should be in. But you definitely need the charge. So what is happening in this bond and what's happening with our electrons? Well, if we look at the lithium configuration, lithium pretty much just gave away its valence electron, which means lithium from its neutral state went from 3 electrons down to 2 electrons. And once again, if we look on the periodic table, number 2 is our friend helium, which is a noble gas. So by lithium giving away its electron in this situation, it's able to achieve the same electron configuration as a noble gas and helium. Now, what happened to our fluorine? Fluorine's all good because, as we know, in the p subshell, you could put 6 electrons, right? And to start with, fluorine only has 5 electrons. So that electron that's coming in from lithium has a place to go. It has a place to go right about there. And that will now give fluorine that extra electron, 1s2, 2s2, 2p6. That is 10 electrons. And if you look on the periodic table, number 10 is neon. So by fluorine gaining that electron, it's able to go forward on the periodic table to the noble gas that comes after it and achieve noble gas configuration. As I mentioned before, pretty much the goal of bonding, right, is to get everybody to the same electron configuration as the noble gases. Here again, this is achieved by the lithium giving away its electron so it can back up on the periodic table to the noble gas that comes before it. So lithium basically goes backwards to helium, and fluorine goes forward to neon by gaining the electron. Any questions on that there? All right, let's take a look at another one here, which is, that's the one we just did. So as I mentioned before, no sharing of electrons in an ionic bond. That positive negative attraction is what's holding those units together. And again, that is pretty much your ionic bond there, positive negative attraction. Take a look at calcium oxide. Calcium is group number 2, which means it has 2 valence electrons. It also has an electron configuration of argon 4s2. And again, these right here are the valence electrons, the highest energy. We take oxide, which is oxygen. Oxygen is group 6 on the periodic table. And if we do electron configuration for oxygen, 1s2, 2s2, 2p4 in this case. And right here are the 6 valence electrons in oxygen. So again, in the same situation here, we have a metal and a non-metal coming together. That again is always going to tell us it is going to be an ionic bond. And that also should tell us that the metal is going to give away its electrons. So the calcium here is going to send an electron over. In the case of calcium, it has not one electron to send. It has a second electron that it could also send over to our oxygen. The reason for that is if you look on the periodic table where calcium is located, calcium is right here. It is trying to get back to argon, right, by losing electrons. If it loses just one electron, where does it end up? It ends up at potassium, which is not a noble gas. So definitely calcium is going to want to lose its second electron so that it can end up back at argon. It's going to be able to do that because, again, these are both valence electrons. So it's going to get harder to lose the second one, but it will be able to do so. The result of that is calcium now will end up with a +2 charge because it gave away 2 electrons. The oxygen in this case will actually pick up 2 electrons. I'll just circle these 2. And because it gained 2 electrons, it now will become a -2 charge. And once again, what's holding that together is the attraction between the positive ion and the negative ion in this case. And that is what's holding that together. There is no sharing of electrons here. So once again, we can see what happens to each of these guys. If we take a look at calcium, it's going to give away those 2 valence electrons, which is going to take calcium back to 18 electrons and the same electron configuration as argon. The oxygen has room again in the p orbital here. It only has 4 electrons to start with. It could hold 6, so it has plenty of room for those 2. And it will then end up being 1s2, 2s2, 2p6, or that's going to be neon's configuration. So once again, both of these elements are able to achieve noble gas configuration by losing electrons and gaining electrons in this case. Any questions on that there? Once again, we do need to include the charges here in our drawings of an ionic compound or ionic bond. Now, what would happen if we kind of put together the 2 of these things? So let's take a look at if we took calcium, which has 2 valence electrons, argon 4s2, again, these being its 2 valence electrons. And let's say we put it together with fluorine, which is group 7, and has 7 valence electrons in this case, 1s2, 2s2, 2p5, and again, those are the 7 valence electrons in this case. Same thing's going to happen here. Our calcium, which is our metal, and our fluorine, which is our nonmetal, is going to cause those electrons to be transferred. He's going to send an electron over. At this point, can that fluorine take any more of those electrons? It is actually going to be full at this point, right? Because now it will have 8 electrons. So that's a little problematic for calcium because, as we just talked about, if calcium only gives away 1 electron, it will move back to potassium, which is non-noble gas. So calcium really wants to give away both electrons to be happy. So in this case, 1 fluorine is not going to be enough. We actually will need a second fluorine atom that has the same electron configuration. And that second fluorine can take our second electron from our calcium. And that's going to make calcium really happy in this case because calcium will now have a +2 charge. And what happens to each of these fluorines here is each one only gained 1 electron, not 2, but just 1. So it has a -1 charge. And we have another one that gained just 1 electron, which will make a -1 charge. Again, it's the attraction between the positive ions and the negative ions that hold that together. But in terms of all 3 of these atoms here, or these elements, they all are in good shape at this point because calcium was able to get rid of both of its valence electrons, 1 to each fluorine, and that's going to allow calcium here to end up in argon's configuration. Each of our fluorines had a spot there in the p orbital to accept an electron, and they're each going to be able to accept an electron, and both of them will end up as 1s2, 2s2, 2p6, our neon's configuration, and it's the same for this guy as well. So all 3 of those things, the 2 fluorines and the 1 calcium, have all gained enough electrons for all 3 of them to be stable and reach that noble gas configuration. Any questions on that? Now, why is this important? We're going to talk about naming after this chapter, but we got into it a little bit at the end, I think, of chapter 4. If you remember what we talked about, when you have a positive ion and a negative ion, and you put them together, the goal is to put them together so that the overall charge is 0. The simplest way to do that. So if we were to put these guys together, we would need, again, an extra 1 there, which gives us -2 to balance out that +2. And that will give us our proper formula here for calcium fluoride, which is CaF2. The reason why we take a positive ion and negative ion and put them together in the simplest way possible to equal 0 is really the bonding reason here. This will allow everybody to achieve noble gas configuration. If you did not put them together to equal 0 and you just threw them together like so, you would end up with something like this, which means our calcium is going to be short electrons, right? Because it has nowhere to put its second electron and it's not going to be happy. So when we talk about writing formulas for ionic compounds, we always need to equal 0 with the charges in the simplest way possible. And the real reason for that is the bonding reason here. That way we'll get everybody the easiest way to get to that noble gas configuration. Any questions on ionic bonding or how to show ionic bonding? Yeah. And obviously this is always the situation that's occurring when we take a metal and non-metal together. It's like 100%. You don't have to worry about, don't have to think about much other than I know that this is the type of bond that should form when those 2 types of elements come together. So let's then talk about the other type of bonding a little bit here. and that is covalent bonding. And as I mentioned earlier, covalent bonding is different than ionic bonding. And my pictures are a little messed up, so let's redraw them. But covalent bonding happens between two nonmetals. And as we talked about earlier, because they have very similar periodic trends, neither one of them are going to want to give away their electrons. So the best that they could do, again, is that sharing of electrons. And as we will talk about here as we continue on, that sharing could be equal or unequal. But just like, for example, when you see a metal and a non-metal together, that you're going to get a transfer of electrons and going to make an ionic bond. When you see two non-metals together, it should also tell you that you're going to have sharing of electrons in this case, and you're going to make a covalent bond. So these are things you want to think about. So Gilbert Lewis, which obviously is where Lewis structures come from, Lewis dot symbols come from. Basically, I said the idea of bonding is the sharing of electrons. So if we take two nonmetals here, like hydrogen, which, remember, hydrogen is a nonmetal, and we take two hydrogens together, pretty much what's going to happen in this case is neither one of the hydrogens are going to want to give away their electrons because they both basically have the exact same properties here. So we're not going to get any type of transfer of electrons. What we're going to get is these two electrons will decide to be shared between the two hydrogens. And you could do that this way. Or because that is a bond between those two, you could also represent it with a line. And one line represents two electrons or a single bond. As we will see as we continue through, two lines represent a double bond or uh, two pairs of electrons. And we could have a triple bond, which represents six electrons or three pairs of electrons. And that's a triple bond. So why does this work? Well, when we think about those electrons that are now being shared between our two hydrogen atoms, the electrons in the middle here count for the hydrogen on the right, and those two electrons in the middle will also count for the hydrogen on the left-hand side. And because the electrons are between the two atoms, you could also figure there's a nucleus right in each of those atoms, which are positively charged. So as those electrons move between the two atoms, what happens is there's an attraction from those electrons to the nucleus of one atom, but also an attraction to the other atom. And that's what sort of locks those electrons in place between the two atoms, is kind of that mutual attraction to the nucleuses on either side. It kind of locks everything into place. But more importantly, in terms of hydrogen, what this does for hydrogen is the hydrogen on the left ends up with two electrons by sharing, and the hydrogen on the right ends up with two electrons by sharing. And that's really good with hydrogen because earlier we talked about hydrogen should end up with how many electrons? Should only end up with two, right? Just like helium. So the way a covalent bond's able to get everybody to a noble gas is not transferring electrons, but by sharing electrons, what it's able to do is the two atoms in that bond, each of them will still be able to achieve noble gas configuration by sharing those electrons rather than transferring them. That is what is referred to as a covalent bond. And again, like I said before, it is that kind of mutual attraction between the electrons in the bond and the nucleuses that kind of just locks everything into place and holds everything into place, is that attractive force. Now, if we take a look at fluorine and we put them together, once again here, and I'll draw it a little bit higher so it may be easier to see. We'll go fluorine up here. It's got 7 valence electrons. And we got fluorine over here with 7 valence electrons. Once again, fluorine, identical properties. So they're going to share those electrons. The result of that, again, is you could draw it like so with all dots. Or it is very, very common where there is a bond that we use a line instead of the dots, but you can really do it either way. So it's your preference for the bonding sort of part of it. If you want to use a line or you want to use two dots or whatever it may be, I would again say most people will use the lines and the dots for the kind of outside ones. So how does this help fluorine sort of achieve what it wants to achieve? If we look at the fluorine on the right here, it has 8 electrons, and those 2 in the middle will account for the fluorine on the left, which will give this guy 8 electrons. And once again, here through sharing those electrons, they both are able to achieve noble gas configuration, and that gets them both to that really stable state. So again, it's the same sort of idea. The same goal is to get to the group 8 over there on the periodic table, just in a covalent bond. How we do that is through sharing rather than an ionic bond that we do it through a transfer of electrons. Any questions on that there? Now, speaking of electrons, there are 2 different types of electrons that we see when we draw these type of pictures. These are sometimes referred to as Lewis structures here. And when we draw these type of pictures, there are 2 different types of electrons. And once again, I'll copy it up towards top so we can see it again. All of the electrons that are represented in this picture as pairs of electrons or dots, they are not involved in any type of bonding. And I know they're not involved in any type of bonding because there is no other element on the other side of them, all right? And as it shows on the bottom there, these guys, which are not involved in bonding, have a very creative name. They are known as non-bonding electrons. Or if you're a little older like me, some people call them lone pairs. I think people still call them lone pairs, but a lot of books nowadays will roll with the non-bonding electrons versus lone pairs. So if somebody says lone pairs or somebody says non-bonding electrons, they're talking about the same thing. They're talking about the dots in your picture that are not involved in any type of bond formation. That also leaves us one other type of electrons that are there, and that is actually this one here, which is part of a bond. And remember that that one line represents 2 electrons or 2 dots and a pair of electrons. And this has a very creative name as well. That is known as bonding electrons. So non-bonding electrons are electrons not involved in any type of bond formation. Bonding electrons are involved in bond formation. And again, the bonding electrons are typically drawn with the line, but it is not incorrect or it's not wrong if you use dots for bonding electrons too. So if you want to use dots, you can. But again, most people kind of use those lines. Any questions on either of those types of electrons? So a Lewis structure represents basically covalent bonding by using our Lewis dot symbols. Again, only the valence electrons are shown in these sort of pictures. You should remember that each of these elements have their core electrons still involved, but we only represent the valence electrons in these type of pictures. Another example of what we've been talking about is water. If we were to draw the Lewis structure for water here, and I'll use all dots here to begin with, like you can see on the bottom there, you could also just draw it like this as well. What's happening in this case through sharing of electrons is our hydrogen right here sharing electrons with our oxygen will get 2 electrons. Our hydrogen on the right will also get 2 electrons through the sharing. And now the oxygen in the middle that is sharing with both hydrogens will now get 8 electrons. So again, in this particular case, all 3 elements are sharing electrons. And by sharing electrons, that's going to allow all 3 of these elements to get to that noble gas configuration. The oxygen gets to 8. And again, as we've talked about, each of the hydrogens are able to get to 2. Any questions on that there? Now, obviously, we've talked about it here, and 8 is a really important number in bonding. Officially speaking, 8 is what is known as the octet rule. The octet rule means everybody's going to continue to make bonds until they have 8 valence electrons around them. So they will continue to do so and continue to make bonds until they have 8. Our one exception, right, as we've talked about, is hydrogen, and that is sometimes referred to as the duet rule. And hydrogen will only get to 2 electrons. It should never have, again, more than 2 electrons. So those are 2 really important rules when you're doing bonding. Sometimes people, when they draw things, get carried away and just kind of keep adding things. So definitely shouldn't go over 8, and definitely shouldn't go over 2 for hydrogen. And you'll hopefully be in good business on that. Now, to reach the octet rule, in some cases, it only requires a single bond. So some cases, single bonds is all you need to get everybody in a covalent sort of compound, a covalent bonding to 8. And as I mentioned earlier, a single bond is one line that represents basically a pair of electrons or 2 dots. As we can see here in our fluorine, that is enough to get everybody to 8 electrons around it. Now, sometimes single bonds is not enough to get everybody to 8 electrons. And sometimes you actually do need to go to a double bond. And a double bond is when you got, again, 2 lines that represent 2 pairs of electrons or 4 total electrons. For example, I'll draw it up here a little bit higher so you can see it maybe easier. If we look at carbon dioxide, it actually needs to, and I'll draw them all in dots so we can see what's going on there. It actually needs to make not one, but actually 2 double bonds to allow everybody to be happy in this case. And if we look at what's going on here, by sharing with the carbon, that oxygen gets double bonded and ends up with 8 electrons around it. Same thing on the other side. This guy, by double bonding with the carbon, will also end up with 8 electrons around it. Now, that also helps the carbon because by double bonding not on one side but both sides, it is also able to reach 8 electrons. So in this case, actually 2 double bonds are actually needed to get yourself to the octet rule. If you try to do all this with single bonds, you will end up with a picture that looks like this. And this carbon in the middle is not happy because it has only 4 electrons around it. It has 2 here and 2 here, and it's way short of 8. So again, sometimes single bonds is not enough to fix it. Sometimes you do need to go to a double bond. And sometimes even a double bond is not enough to fix the situation. And then you actually need to go to a triple bond to do so. So that's the case, for example, for nitrogen, which is triple bonded here. And what we see is this right here on the left counts for it. It has 8 electrons. That triple bond being shared in the middle also counts for the guy on the right, which has 8 electrons as well. So sometimes a triple bond is necessary. I will say this now, and I probably will say it again later, but it does bear repeating. When people start to draw Lewis structures, they for some reason always want to like double bond and triple bond like right out of the box and go, it must look more chemistry like if you put more lines on it and stuff like that. So as we will talk about, there is a specific sort of order when you draw these structures that you want to follow. And usually the order is you want to kind of try it with all single bonds first. And then if somebody doesn't have 8, then you want to maybe try to fix it by doing a double bond. And if that doesn't work, then you want to kind of fix it by doing a triple bond. You definitely don't want to just double bond and triple bond out of the box. That usually will lead you to a bad picture, not enough electrons, too many electrons. So just if you have that sort of habit, try not to do that. It's a very common thing. I think people just think it's got to do that because it just seems more chemistry-like with all those lines. So now that we understand the sort of the sharing of electrons, we're going to talk about a property here that really determines how the electrons are going to be shared. And we talked about electronegativity earlier today when we were talking about periodic trends. And once again, a reminder that the electronegativity is the ability of an atom to bring electrons towards itself. And if you remember what we talked about on the periodic table, increases as you go up and to the right, decreases as you go down. And it is our element there, fluorine, that is the most electronegative element you could have. And if you look up there on the periodic table, like I said earlier, fluorine is as far up and to the right on the periodic table that you can go, other than noble gases. And once again, noble gases are not looking to do anything because everybody's trying to be like them. So they're not really even looking to do any much work. In fact, sort of considered a lot of times, noble gases don't have any electronegativity, like a value of 0, because they're not really looking to gain electrons or lose electrons. They're kind of happy the way they are. So electronegativity really is what allows us to decide how those electrons are going to be shared equally. So if we take a look at an example we just talked about, which is the bond between our hydrogen atoms, when we think about how those electrons are going to be shared between the two hydrogens, one thing we know for sure is they're both hydrogen in this example, right? And those are the two ones that are sharing electrons, which means because they are the same element, they definitely will have the exact same electronegativity, which means they will have the exact same pull on those electrons as each one does. You could think of this kind of like tug of war, like you got a rope, right, on, and then like a little flag in the middle, right? People are pulling this way, right? People are pulling this way on the rope, and you're trying not to get pulled into like a mud pile in the middle or something like that, right? So in this case, what we have is, because we have hydrogen on the right-hand side, hydrogen on the left-hand side, they're going to equally pull on that rope, right, of those electrons. And what's going to happen is nothing much is going to happen, right? They're going to not really move one way or the other. And the end result of that is we're going to end up with an electron distribution that's going to be fairly equal. And they're going to share those electrons equally. So if my little blue here is the electron sort of density, it's going to be equally shared on both sides of this bond. And we are going to result in equal sharing of the electrons. And this type of bond, when that happens, is what is referred to as a nonpolar covalent bond, or a nonpolar bond. Now, I will say most people will probably just roll with nonpolar bond. It's assumed that you understand it's a covalent bond and there's sharing of electrons, but it is a nonpolar covalent bond, or a nonpolar bond. The consequence of these electrons being shared equally is there is no like charge. It's kind of like a neutral bond. There is no positive side, there's no negative side, because the electrons are really distributed equally around each of those atoms. This would be basically neutral in terms of any type of charge. So there is no negative side or positive. Yeah. Say it one time. Yeah. So the official name for this type of bond is a nonpolar covalent bond. But because people just assume that it is a covalent bond because it's two nonmetals, a lot of times people will just straight up just call it a nonpolar bond, but it is the exact same thing. Yeah. Other questions? Okay. Now, what will happen though if I took out one of the hydrogens and I replaced it with a different element? So let's say that I took out one of the hydrogens and I replaced it with a fluorine. And now we have a bond between these two things. Really long bond there. And we are now going to have some difference in electronegativity. For sure, what we know is fluorine is the most electronegative element you could have, which means when we look at that bond between the hydrogen and the fluorine, if I were to basically show where the electrons would be, Should the electrons be closer to the hydrogen or the fluorine? Which one should that be near? Fluorine is more electronegative, which means it wants to bring electrons towards itself. Because fluorine is more electronegative, it's going to actually pull those electrons in that bond a lot closer to the fluorine. And there's going to be a lot less electrons hanging out on the hydrogen side of this bond. And if we look at the result of what happens because of that, we would expect in this case, because electrons are negatively charged and they're hanging out closer to the fluorine side, that the fluorine side will actually gain a partial negative charge. That's a delta negative symbol. It means a partial negative charge. And because the electrons are moving away from the hydrogen, what that's going to create is a partial positive charge here. And this also can be represented with an arrow. And this arrow that you see a lot is what is referred to as a dipole arrow. And the arrow always points to the more negative side of the bond. And the back part of the arrow, which makes like a plus symbol, is always towards the positive side of the bond in this case. Now, why is it just a partially positive charge? And why is it a partially negative charge and not a full positive or full negative charge? The reason for this is there is still sharing happening here. So the electrons have not fully transferred from like the metal to the non-metal like we see in an ionic bond, and we get a full transfer of those electrons. Here, the hydrogen is still hanging on. So if you want to go back to the rope example, the hydrogen is barely hanging on, but that fluorine is dragging him across the field there as he tries to hold on, but he's still able to hold on to the rope there. So he's still able to hold on to the electrons. So we still have our electrons being shared here, which is why we don't get a full positive charge on the hydrogen and a full negative charge on the fluorine. We get these partial positive and partial negative charges because there is still some aspect of sharing. This type of bond here is what is referred to as a polar covalent bond, or just commonly referred to as a polar bond. And it results from unequal sharing of electrons. Any questions on that there? So electrons could definitely be shared between two nonmetals, and that sharing, based on really the difference in electronegativity between the two atoms, can be shared equally or unequally, depending if there is a big difference in electronegativity. And again, that is essentially what we just talked about there. We'll have more electron density towards our fluorine. And again, that's going to create a polar covalent bond or just a polar bond. It is basically referred to. Again, we're going to get that separation of charge that's going to occur. It is not going to be a neutral charge like we talked about with a nonpolar bond. Here, we definitely will have kind of a charged part of the bond. Some part will be positive, one part will be negative. As we'll learn in later chapters, that's actually a really big part of what allows, for example, certain molecules to be, say, soluble in water or mix with water, or why certain ones will not mix with water or will not behave well with water. So these sort of charged parts of these bonds can play an effect in how things interact with other molecules. Could also play a really big role in things like boiling points and melting points, depending on what type of bond you got going on. All right. So to sort of summarize the three types of bonding that we've talked about here so far, on one end of the extreme, we have an ionic bond, and that is always between a metal and a nonmetal. And we always get a transfer of electrons from the metal to nonmetal, again making our cation that's positive and our anion that's negative. And this is going to be held together by no sharing of electrons. And that electrostatic attraction is what holds it together. An example of that would be any ionic compound like sodium chloride would definitely be an example of that. If we go on the other end of the extreme, we have a nonpolar bond. That is going to be between two nonmetals. That is going to be equal sharing of electrons. And an example of that would be any of those two that we've been talking about, H2 or F2. And sort of in the middle of those two types of bonding is our polar bond, our polar covalent bond. Also between two nonmetals. In this case, we have unequal sharing of electrons. And again, that's going to result in, as we talked about, a bond like we see here, where one side is going to be more negative than the other because of the unequal sharing of electrons. So one end of the extreme on ionic side, we're just going to give away our electrons, full transfer. Other end of the extreme, we're just going to share those things perfectly equally or equally. And in the middle, we have not perfect equal sharing, but not so unequal sharing that the electrons actually transfer. We have some type of sharing still, but definitely not equal sharing of electrons. Any questions on any of those three types? Both of these are. So both of these are covalent bonds. Yeah. So anytime you got two nonmetals together, they're going to be covalent. Just like when you have a metal and nonmetal, it's going to be ionic. So those are kind of what you want to think about. And like I said, a lot of times people will just call it polar bonds or nonpolar bonds, but they are inherent covalent bonds because they're two nonmetals that have sharing of electrons happening. And just like with our ionic bond, definitely always going to have that transfer and no sharing of electrons. Other questions? So how do we know that the electrons are going to be shared? We definitely know we're going to have sharing of electrons if it is a covalent bond, and that's straight up two nonmetals in a bond, covalent, going to share. But how do we know how those electrons are going to be shared? Are they going to be shared equally? Are they going to be shared unequally? And it really is electronegativity that helps us decide how those electrons are going to actually be shared between those two atoms in that bond. Electronegativity is based on electron affinity and ionization energy. Fluorine has high electron affinity and high ionization energy, which means it likes to gain electrons and it takes a lot of energy to remove electrons. So that's why it has high electronegativity, it's able to bring those electrons towards itself. Sodium is the opposite. It has low electron affinity and low ionization energy. So sodium is not looking to gain electrons, nor is it looking to hang on to its own. So that's why it has low electronegativity. So we could actually calculate the electronegativity to help us decide what type of bond we're going to have. And a guy by the name of Pauling came up with an actual scale for electronegativity. The Pauling scale runs from 0 to 4. 4 is the most electronegative, and 0 is not so much. Yeah, so pretty much no electronegativity if you're 0. So we could calculate what is sometimes referred to as delta En, and that is abbreviation for the change in electronegativity values. So there is a table that we're going to see in just a second that has the electronegativity values for the different elements. And you can basically just go to that table and find the two elements that are involved in that bond and basically just subtract the two values that you have. You can subtract the higher value from the lower value, and that way you always get a positive number. So if you do that and you get anywhere from 0 to 0.4, that is considered a nonpolar covalent bond. That's going to tell you that you should expect the electrons to be shared equally within that bond. If you have above 0.4, which is about 0.5, to below 2, that is going to give you some type of polar covalent bond. which will tell you that the electrons are not going to be shared equally in that case. Now, this one you really don't need, but typically above 2 is going to produce an ionic bond. Once again, the reason you don't really need it is twofold. One is if you know it is a metal and a nonmetal, that's all you need to know. It's going to be ionic. So you don't even really need electronegativity values to help you decide if it's going to be an ionic bond. Secondly is, as we will see in a second, there is a lot of cases or a number of cases where you can put a metal and a nonmetal together and they will actually have an electronegativity difference of less than 2, but it's still an ionic bond. So that 2 number is just a general number. It's not perfect for all ionic bonds. So the thing you want to remember is, as we've been talking about, if you have a metal and a nonmetal, it's going to be an ionic bond. You really don't need electronegativity. So I would recommend that you really should just use the electronegativity values for covalent bonding to decide how they're going to share the electrons. Is it going to be equally or unequally? Another term that you sometimes come across when you're dealing with this stuff is if you have a difference in electronegativity of 0. That is what is sometimes referred to as a pure covalent bond. And a pure covalent bond is a nonpolar bond, but it is like as perfect equal sharing as you could have, basically. Yeah. Now, there is degrees of what is considered equal and unequal. We could go all the way up to 0.4 that's still considered equal, but in reality, if you have a 0.4, it's not perfectly equal sharing of electrons. It's going to go one way or the other in that bond, but not enough that is considered polar. So it's still considered nonpolar. So electronegativity, as we talked about, increases as you go up to the right, decreases as you go down. So let's just take a look at a table. So this is one like you have in your book or a similar one, but these are all the different electronegativity values. And you can see as you go from left to right on the periodic table, and especially up to the right, the electronegativity values increase. And there's our fluorine up and to the right at a value of 4. As I mentioned before, you typically don't see noble gases on an electronegativity table because they're not looking to do much. And they typically, if you need to use it, typically you would use a value of 0 for them is typically what you would use. So if we take something like the bonds we looked at previously, which is sodium chloride and the bond between HF and the bond between F and F, if we wanted to calculate our difference in electronegativity values for sodium chloride, we would go find sodium, and sodium is right here, and it has an electronegativity value of 0.9. Chlorine is to the right here and has an electronegativity value of 3. The difference here is 3 minus 0.9. Again, just taking the larger number minus the smaller number, that gives us a 2.1 difference. That 2.1 difference is above 2, and it would tell us, if you weren't sure, it is an ionic bond in this case, no sharing of electrons. Now, again, the reason why this is maybe not the best thing to use for ionic is there is definitely places where you could get less than 2. For example, if you took lithium and you took bromine, lithium and bromine, lithium is 1, bromine is 2.8. So if I do the difference in electronegativity, that's 2.8 minus 1 is 1.8. That is obviously less than 2, but it's still an ionic bond. So again, I would not even worry about electronegativity values for an ionic bond. Just no metal, non-metal. That's all you have to worry about in that case. Yeah. Say again. Honestly, in this case, what you really want is just the difference. So you really just kind of want a positive number. So you can always just put the larger one first and minus it. Even if you get a negative, now you can ignore the negative. In this case, it's actually just the number part that's important. So even if you did it and got a negative, just the number part's the part you want to look at. Yeah. Now, if we look at our fluorine bond here, this fluorine is 4. And this fluorine would be 4, which means when we do our difference in electronegativity for this guy, that's going to be 4 minus 4, which is 0. And definitely that 0 falls in the 0 to 0.4 range. And that's going to give us a nonpolar bond, equal sharing of electrons. as that, again, that falls between the 0 to 0.4 range for nonpolar. Right? That would also be considered, again, a pure covalent bond because the difference in electronegativity in this case is actually 0, and that's going to give us perfect sharing of electrons. Now, if we take a look at our HF bond, our H is 2.1, which right here, and our fluorine is also 4. So again, just taking the larger number first, 4 minus 2.1 gives us a 1.9 difference. 1.9 difference falls between that 0.5 to below 2 range, and that is polar. So this is going to be a polar bond. It's going to be unequal sharing of electrons. The arrow, that dipole arrow that you could draw, should always point to the more electronegative. So you could clearly see here 4 is more electronegative. So we should point that arrow towards the fluorine. And again, this indicates that that is a polar bond. We do not use the arrow for a nonpolar bond. So the arrow is only used for polar bonds to indicate the difference in charge between those two atoms within the bond. If you have a nonpolar bond, you do not use any differences or that arrow for it because you have equal sharing of electrons. Any questions on how to use that there? So why don't you try some here? I got another chart maybe? No, I don't. I'll use this one here. I'll just clear these out. So why don't you use the difference in electronegativity to decide if the following bonds are polar, nonpolar, or ionic. So we'll do potassium and chlorine. We'll do nitrogen and oxygen, the bond between sulfur and oxygen. We'll do the bond between carbon and hydrogen, and we'll do the bond between, we'll do carbon and sulfur. Why not? All right, so to use your difference in electronegativity, again, if it is 0 to 0.4, that is nonpolar. 0.5 to below 2, polar, and above 2, typically ionic. All right, so take a moment, use the chart there, and figure which type of bond each of them are. Okay, so let's take a look. So again, we're just going to pull the numbers off the table for each of them involved in the bond and just subtract it. Again, like I said earlier, you could kind of do the larger number minus the smaller number. So potassium there is 0.8, chlorine is 3. So I'll just do right here, difference electronegativity, 3 minus 0.8, 2.2. It is definitely going to be ionic. But once again, we really didn't need it for that one because potassium is a metal, chlorine is a nonmetal, so you should know it's ionic just from that. So we'll take a look at the next one, which is nitrogen and oxygen. Nitrogen is 3, and oxygen there is 3.5. So if I do the difference in electronegativity for that one, it's going to take the larger number minus the smaller number. It's going to give me 0.5. 0.5 is above 0.4, which means that this will be a polar bond. And it should have that arrow pointing towards the oxygen as it is more electronegative. And that means the oxygen in this bond will be more negative. The nitrogen in this bond will be more positive because of the difference in electronegativity. Any question on those two there? Taking a look at sulfur, which is 2.5, and oxygen, which is 3.5. So definitely difference in electronegativity here. 3.5 minus 2.5 equals 1. That definitely is above 0.4, and that would mean that this also is a polar bond. Also, the arrow here would point towards the oxygen as it is more electronegative, and the oxygen would be more negative in this bond, then the sulfur will be more positive. Looking at carbon and hydrogen here, carbon is 2.5. Hydrogen is 2.1, so my difference in electronegativity, 2.5 minus 2.1 is 0.4. 0.4 is the top tier of nonpolar, so this would be a nonpolar bond it would be considered that electrons would be shared equally here. Is this a perfect equal sharing of electrons? This is not, because it's not zero. So in this case, actually the carbon is actually pulling a little bit more of the electrons towards itself. It is not enough to be considered polar. And that's really because carbon and hydrogen is the major bond, or one of the major bonds in organic compounds that are nonpolar. So carbon, 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 hydrogen is nonpolar, which is why the cutoff actually is 0.4. Lastly here, carbon, which is 2.5, and sulfur, which is 2.5. So if I do the difference in electronegativity, that's going to give me a 2.5 minus a 2.5. That is actually a difference of 0. And that means that this bond here is going to be a nonpolar bond. And it brings up a good point that you can definitely have two different elements that actually share the same electronegativity and can be nonpolar. Why does that happen? They are what are referred to as being diagonal on the periodic table. Not perfectly right below each other, but over one. So copper, our carbon is further up, but sulfur is further to the right. They cancel out their differences and they end up with the same electronegativity value. You also see that, for example, with nitrogen and chlorine, that kind of diagonal relationship. So you sometimes will have that diagonal relationship. Again, it's not right below it, but over a little bit to the right. And they can have the same electronegativity, which will give you a nonpolar bond. First off, any questions on how to use these values here? Now, do you always need these values to make a good guess as to whether or not you're going to have a polar bond or not? The answer is no, especially if you are basically comparing two things in the same row. So, for example, we did nitrogen and oxygen, and nitrogen and oxygen are in the same row on the periodic table. They are right here. And oxygen is further to the right, which means it's more electronegative. And because of that, you could probably know it's going to be a polar bond. So if you're comparing two things in the same row and they are located at different spots in those rows, the one further to the right will be more electronegative, and it will probably lead to enough of a difference that it's going to be a polar bond. So it's a pretty safe bet. Now, we also did sulfur and oxygen, which is actually in the same group here on the periodic table. And electronegativity increases as you go up the group. And if you're comparing two things in the same group and there's one that's further up than the other, it is also a pretty safe bet that it's going to be a polar bond. And the one obviously further up in the group is going to be more electronegative. So a lot of times you don't really even need the numbers. In a lot of cases, you can make a pretty educated guess based on where they're located on the periodic table. Clearly, these numbers would be provided for you if you needed them, and you just need to know how to use them. Any questions on that? There, yeah. All right, we're going to lay that